Okay, so we're off and running here. So we're looking at the calendar here, just kind of get you up to speed. Where should you be at? Uh, so hopefully you're done with the stuff from October 13th. October 16th tonight and 18th is coming up. So I'm going to take a look at. Oh wow, tonight's Wednesday. Tomorrow's Thursday. Okay, good. So we got some time. We're good to go. So we'll do these sections here. Now, if you don't do it tonight, that's fine. Do it tomorrow, Friday. Really, what we're looking for is yeah, what we're looking for is by Sunday, be caught up with all this. Now it looks like it's a lot, and it is. I mean, it's a fair bit of amount. Hopefully, you're finding it not too terrible. So we're going to finish simplifying radicals and complex numbers tonight. Then this stuff right here, we can pretty much, one of them we've already done. That's the good news. The good news here is we've done this one. You just don't realize you've done it, but we've done it. And so this stuff right here is solving quadratics by factoring, by quadratic formula, and looking at the Pythagorean theorem. Again, that's stuff that you actually already know. It's just putting the pieces of the puzzle together. So again, it's not new material. It's just sort of, hey, what skills do you have, and how do we apply them in the context? Okay, so let's take a look at simplifying. Let's finish up at least simplifying radicals, and we made pretty good headway through the process for everything. We're taking a look at how do you deal with radicals with a square root and then with a cube root. So when you have a fraction, just remember the way that you do it is you give each one, the top and bottom, its own radical, and you simplify each of them, separately. So simplify the square root of 52 and then the square root of 10 separately. And we talked about those techniques, but just to remind you of that. We also looked at how do you deal with the fact when you have numbers and variables inside the square root or inside a cube root. And then how do you deal with it when you got a fraction? Still the same thing. Give them each the top and bottom their own, and then simplify the radical as you normally would. We also did yesterday, we took a look at how do you do the cube root of a negative number inside. And essentially what it boils down to is, excuse me, you're looking for the perfect cube. Let's do this one. This is a pretty good one. So how would we do the cube root of negative 81? So ask yourself, what is the perfect cube? Is there one? A perfect cube that goes into 81. A perfect cube that goes into 81. And so you want to find the factors of 81, if you will, that go into 81, and the perfect cube factor will be what? It'll be negative 27, and then times 3. 27 times 3 is 81, and just attach that negative sign in front of the perfect cube part, in front of the 27, okay? So then, like before, you give each one their own house, their own radical symbol, so it becomes the cube root of negative 27, and then the cube root of 3. Now this one, the first part, cube root of negative 27, what does that simplify down to? What raised to the third power will give us negative 27? Well, what raised to the third power will give us 27?
Oh, 9. I'm sorry. Is it 9?
Not 9, but what 3? So you need copies. Something sometimes something times something times something gives me 27. What's that something?
3?
3.
3. And because it's negative 27, it's negative 3.
Okay.
And so then just bring down your cube root of 3. There's a lot of 3's in this problem. So that's the answer for this one. So essentially, you're really just looking for the perfect cube and then just attach the negative in front. It works the exact same way. The negative doesn't change the process. It just changes the look of it. See what else they got cooking for us. This one is just a matter, by the way. Uh, so this says a resistor. 24,000 is a resistor. That's the value of R. Oh, I see. Yeah. This is telling you over here what each one is measured in. Okay. So if you see ohms, OHMS with that little omega symbol, that's telling you, hey, when you see that, that's the value of R. 6.5 watts, oh, watts is up here, that's the P variable, that's the value of P. Okay, so then you've got the value of P and R, so this is the formula you're going to use. E squared equals PR. Plug in your value of P and R is what, 24,000 times 6.5. Break out your calculator. I have no idea what that is. 156,000. And then how would you find the value of plain old E? How would you find the value of plain old E? So
You
this
would
is, let me
square the
type this now.
156,000 and the E square.
Right. So to find E, you would then take the square root of both sides. Because the square root, the reason why we do that, the square root is going to cancel the squared because they're opposites. The square root's going to cancel the square. So the square root's going to undo the square. And so then you put this in your calculator. Square root of that is, so the answer is 3, this one here, for completeness sake, 394.97. We'd have to round it. Why 7? Because it's telling us to round to 2 decimal places. So the point
Okay,
here, when you have,
wait, hold on. I have a question.
Mhm.
So, if we have both R and P, why wouldn't we use the top equation? Because they also have P and R.
Oh, let's see, voltage. Well, this one says, I'm sorry, this says what's the voltage? And so E is the voltage.
Okay, that's what happens whenever you don't read. Make sure you read the question.
Well, I'm glad it worked out that way because I didn't read the question either. I luckily picked that second one. So if they had asked you what's the current, then you would use I. So my point is when you look at this one, you want to break it down. Go kind of same thing. You kind of want to look for connections to it, and that's kind of how the way I would do it is you if you don't take this is a physics formula. It's every electrician knows this one. Uh, but anyways, if you didn't know that, you would want to dissect. Here's what I know. I'm using these symbols, kind of connect the pieces, if you will. Okay, I'm trying to see if there's a special problem I'm thinking of in my head, and they're not doing it.
If you have
Okay.
time, can we do one more like that? Because I was writing down as fast as I could, so I missed kind of like the process. So I'm just gonna watch. Or it's being recorded, you said?
Mm-hmm.
Okay, I'll go back and watch it on the recording
Okay,
so I don't slow you.
that's fine. All right, so let me then go to. Nope, not it. Wrong one. Wrong button. Let me go to then. So we've actually done. So fortunately, they didn't do the thing I thought they were going to do. So that's great for us because that kind of reduces the complexity, if you will. We don't have to get in. I was about to get into some things that were not going to be fun. Okay, so then let me move to the complex numbers. So we've done just a kind of working with radicals. We've looked at how to evaluate radicals, with numbers inside. Simplifying radicals, perfect squares, perfect cubes, and if you have something that's not perfect, you would try to factor it into a perfect, something with a perfect square, perfect cube factor. And then we looked at, oh, excuse me. Then we looked at how to do variables. So that's pretty much it. Let me move to complex numbers then, because that's not too terrible. It's related, but not. It's also your work with like terms back in the day at the beginning part of the course. Like terms. That's how you're going to do complex numbers.
Back in the day, like we
A
learned
month
this in
ago.
the 1900s.
Yeah. 1900 hours ago. Okay, so we've sort of talked about complex numbers already, haven't we? Complex is the same thing as not real or non-real. And we introduced those already, and we said, well, whenever you have the square root of a negative number, like the square root of -4, that's going to give us something that is not real or non-real, and we generalized it too. We said it's anytime you take the even root of any negative value, so the square root, the fourth root, the sixth root, but we're not going to get into that. We're just going to stick with the square root. Complex is specific to the square root. So you have something like this, or maybe you'll have something like this, okay? You could have something like that. So what we do is we don't like the negative sign inside. So remember, whenever you see a negative sign, what is a negative sign? At the end of the day, fundamentally, a negative sign is just -1 times that number, right? Y'all remember that? Follow along? Okay, good. So I just want to don't want to lose you on that point because that's a critical point. Okay, so then just like we've been doing before, let's give the -1 and the 4 its own radical. When we do that, we know how to do this, don't we? What is the square root of 4?
2.
2. Boom. There it is. So what are we going to do with this thing out here? And you probably know the answer. You've probably seen it before. If not, that's okay. What we're going to do is we're going to define this. We're going to say, we're going to let the letter I represent and be defined as the square root of -1. And so what we're going to do is we're going to take this thing right here and we're going to turn it into I. Now, keep in mind, this is fundamentally what? I times 2. And so what we're going to do is we're going to rewrite this and we're going to treat the I like a variable. And so we're going to write it as 2I. Just like you would do 2x, 2y, 2p, 2q, it's 2I. But the I has a specific meaning the square root of -1. So how would we do something like this one then? The square root of 9. In a similar fashion, what I'm going to do now is I'm going to write it as 9 times -1. So I can kind of set it up a little easier, a little better. So I make it square root of 9 times the square root of -1. And what does that reduce down to? The square root of 9 becomes what value?
3.
3. And the square root of -1?
I.
I. So that becomes 3I. And what you're going to end up finding is that we treat the I just like we do a variable. And so that all of your stuff with like terms comes into play. Same rules apply. You're really learning nothing new. We're
I
just
have a
reintroducing
question.
old material and putting it into a new context.
Did,
So
did
then
we have to write our eyes like that, or did you just write them to show that it was an eye?
I write it to show that it's an I.
Okay.
Yeah. Okay. So then let's do something like this one right here. How would I do this one? Ideas. What would you say? Negative square root of -4.
I have an idea.
Okay. Is that a Jacqueline? Jackie?
Yes.
Yeah.
So since we already did one a second ago that was just -4 inside,
Mm-hmm.
but no negative on the outside. I'm assuming you would go through the same exact steps until you get to the point where it's outside of it, where it's just your I times your 2, where you turn it around, you put your 2I, and you would put -2I.
Right.
You would tack it on once it's out of the symbol,
Right.
right?
Keep in mind
Okay,
that
so
every time you see a minus sign, that is perfectly correct. Yes. Every time you see a minus sign, it is fundamentally what? -1. And the operation then is multiplication with that and the square root of -4. Fundamentally, that's what's going on. So then we already saw this simplification. This is 2i. And so then just bring down your -1. And so this becomes -1 times 2i, which is what?
thank you.
-2i.
2I.
Yeah. I just want to keep reminding you that every time you see a minus sign, it really is the multiplication of -1. Okay, because they're throwing negatives all over the place, and you just need to. It's -1 times. Okay, so because it kind of changes up the process a little. They're testing you on the negatives. Okay, so then we're getting something like this now. We want to work with the I. We want to work with the I. So before we do this problem, let's look at a couple of examples. Well, I guess I'll just tell you the rules more than anything. I'll tell you the rules because to develop it would be probably a little too confusing. There's a reason why. There's a thing with radicals we didn't do that I thought that we're going to do, but because they didn't do it, if I did it now, it's going to confuse you. So I'm not going to confuse you. I'm just going to give you the rules. How about that? So here's the rules. I is what?
Negative.
Never mind. Yeah, square root of -1. Let me do it this way. I to the 0 is 1. Well, no, let me back up. So we start with I, okay? What do I get when I do I squared? If I is the square root of -1, what is I squared?
Square root of -1 times square root of -1.
Right.
Had to
And I'm
take a
gonna
guess.
write it as the square of -1, okay? The square of -1, just to kind of keep it consistent. One thing to keep in mind is that the square root and the square cancel with each other. So if the square root and the square cancel with each other, what does this give me? -1. The symbol, the square root symbol, and the exponent of 2 on the outside cancel with each other to pop out that -1 from inside. Do y'all see that? So then I to the 3rd power, so I'll write it as -1 to the 3rd, okay? But what is that? Use your, I'm going to change my color ink here. Use your product rule to break it up. So it becomes the square root of -1 to the 2nd power. Don't take notes on this part. This is not important to remember, to memorize. Times the square root of 1. Oh, my goodness. Handwriting is terrible. Okay, now I'll do it. So that's the square root of -1 squared times the square root of -1. That's 3 of them, 3 copies. So this becomes, this thing here is -1. This thing here is I, meaning that this thing becomes -1i. It's all going to come together in a second. And then finally, I to the 4th is what? The same thing as I squared times I squared. But I squared is what? -1. So this becomes what? -1 times -1, which is what? +1. Hopefully you didn't take notes because this is not the rule. Here's the shorthand of it. But that's the development of what we want to do. That's what we're trying to do. So here's what we do. You go in a sequence. I squared is -1. -1. I to the third is -1i, or -I, and I to the fourth is 1. That creates a sequence. Okay? So what do we do? Let's take a look at something like this. How are we going to use that? I to the 102nd power. What you want to do is you want to rewrite it in terms of I to the third, fourth, or something like that. So you look at the exponent of 102 divided by 4. Do long division. So when I do 102 in long division, what do I get? 25, remainder 1.
Why did we divide it by 4 specifically?
Because of the sequence 4.
But why
I'll
did
say it this way. So what happens is, and this is the part I didn't show you. When you go I squared, I third, I fourth, okay? When you go I fifth, that's the same thing as saying I to the fourth times I. So it becomes, so
I get that, but I'm not understanding why we went from 102 to 4. Why did we skip over everything else? Why didn't we do 1i? Why didn't we do I squared? Why didn't we do anything else? You know?
why are we dividing by 4?
Yes.
Yeah. So essentially what's going to happen, yeah, let me see if I can break it another way.
And when you introduced the I on the last thing, I thought it was I is equal to the square root of -1,
It is.
but on this one, I to the second I squared is -1.
It is. I is the square root of -1. I squared is -1.
Okay.
The different is a little different.
Okay.
So think about it this way. So this thing here builds a pattern. So if we go I to the fifth, okay, that's going to be the same thing as I to the fourth times I, okay, because there's 5 I's, 4 of them, and then 1 more. But that's just 1 times I, which is the same thing as what? I. I to the fifth is the same thing as I. So if we do I to the sixth, that's the same thing as I to the fourth times I squared. So it's the same thing as I squared. Don't write this down. This is not going to get you anywhere. I to the seventh is the same thing as I to the fourth times I cubed. So it reduces down to I cubed. I to the eighth is the same thing as I to the fourth times I to the fourth, which is 1 times 1, which is 1. Okay? So my point is that what ends up happening is that you move in a cycle. Every four jumps, you're back to the beginning of the cycle. So that's why we divide by 4, because wherever your remainder is at corresponds to that particular exponent. Okay? So, let me see if we can take all this off. I'm not articulating it fully clear because, yeah, let me just do that. Let me do this. What we're ending up doing is we're still, keep in mind, we're still using our rules of exponents, power rule, quotient rule, product rule, all that jazz. We're using it to break apart. Just like we did it the other day where we were Um, well, so let's suppose I have I to the 12th, okay? That's the same thing as saying what? I to the 4th. If I were going to reverse power rule this, it's the same thing as I to the 4th to the 3rd power, right? Because remember, what's the power rule say? Power of a power, you multiply, and that multiplication is going to give us the 12, right? So why would I want to do this? Because I to the 4th is what? 1, right over here. I to the 4th is 1. So this becomes 1 to the 3rd power, which is 1. Do y'all see this part at least?
I get that. I really do. I'm still not understanding why we have I-102, and instead of using the I that we put on the left side, you use I-4. That's what I'm not understanding. I can get all the adding and extra and how it equals out later. I just don't understand how we got from I-102, and we didn't use the I on the other side, we're using I-4. That's where I don't understand why we jumped.
You talk about this one?
Yeah,
Yeah, before we get to that one, let's do something.
okay.
Let's do a smaller exponent.
Okay.
So at the end of the day, what you want to do is you want to rewrite the exponent 12 in terms of 4s, okay? A product of 4. No, I'm trying something raised to it. So you basically want to see where there's a way that I do it, but there's probably a better way. I'd look to see where I'm at in the cycle. So think of it this way. Let me take this down. Let's think about it another way. Suppose you have yourself a circle, okay, and you have, okay, you're going to make a loop, okay. This is I. This is -1. This is -1I, and this is 1, okay? Just like a clock, you're going around, okay? So if you can, so well, maybe I should have started there. How about this? Let me redraw my circle. I'm going to start in another place. I'll do this. So I'll put 1 here, I, -1, and -1I. So you're starting up here, okay? And so let me do it this way. Suppose I have I to the 15, okay? So you start here at the very top. Start here at the top and go around. Every hash is a step. So 1, 2, 3, 4. So that's what I'm doing, okay? And I want to go 15 steps. 15 steps, increments, okay? So I'm going to go 1, 2, 3, 4, and I'm back. Every 4 steps, I'm back to the top. 4, 4, 4. Do you see that? Okay, so I've gone 4. Now let me go 4 more. So I go 4 again. How many steps have I taken? 2 times around.
8.
8. Let me go 4 more. So if I go 4 more, how many steps have I taken?
12.
12. Okay, so I'm on my 12th. I'm going to mark myself. My 12th step. I need to go 15. So I want 3 more steps. So 1, 2, 3. And I end up right here. So I to the 15 steps. is the same thing as negative 1i.
I caught on to what you were saying like halfway through it.
Say it again.
I said I caught on to what you were doing about halfway through it, about
So
why it's 102.
that's why we
And you
divide this
divided.
thing. That's why we divide this thing by 4. That's why
Yeah.
we divide this thing by 4. So if we had done 15 divided by 4, it's 3. That means 3 rotations around my clock. Remainder 3. This tells me where on my clock am I ending. I'm ending at the 3rd step. This one right here. So let's take this one, 102. 102 divided by 4. How many rotations around my clock do I do? 25 rotations. Remainder what? Remainder 2, because 100 it leaves 2. So that means I end up where? I end up right here on my 2nd step, meaning that this thing is equal to negative 1. So I've got sort of a mess here. Let me see if I can clean it up a little bit. But the whole point, and I guess maybe I hope this was helpful, because it's the first time I've ever done the clock analogy. If you think of it like a clock that just rotates, and the reason why we do this is because it repeats, the pattern repeats. And so just like a clock, the top of the clock is always your starting point, okay? And you ask yourself, how many rotations do you do and where are you at? So if I were going to do I to the 75, I to the 75. How many rotations do we do around our clock is determined by taking 75 and dividing it by 4. So 75, do your long division. That's what? No idea. 75 divided by 4, that's 18 rotations with a remainder of 3. So I'm going to go around this clock 18 times, okay? Go around that clock 18 times, and on my final rotation, I'm going 3 steps, and I'm going to end up right there. That's my answer. So this thing becomes minus 1i. You want to try one on your own?
So we basically, are we going to always divide by 4?
When you're doing something, when you're doing I to a power.
Okay.
I to a power.
Okay.
So then let me give you one. I'll do it here in blue. I to the 80, I to the 81st power.
One I.
Yep. You're going to go 20 times around your clock. So 81 divided by 4. 20 with a remainder of 1. So we have 1 step that we take, meaning we get the answer I. Booyah. I'm going to keep the clock. It sounds like the clock analogy was helpful. Was it better?
When you write it, you don't need to put the one I, you can just put I though for that one?
Yes.
So you would put 1, then I, then -1, and then negative I?
You can do negative
Do you
I.
put
Or
one?
yeah,
I just wanna
I
make
think
sure.
they'll take either one.
Okay.
1i and I are the same thing. -1, negative I, -1i are the same thing. They should take it, but you never know. So that's one thing you're going to have to do. That's just sort of a consequence, because, and the reason this works is because it's a consequence of the way we defined I to be the square root of -1. It's a specific number, the square root of -1. And so because of that, there's a pattern that builds with when you raise I to the powers, and this sort of is the pattern. Every four steps, you're back to where you started. And so then we have things like this. This is interesting. I'll do this one. I to the 11th times 40 over 5I to the 5th. Now, this actually incorporates a couple different things we've already done. You're not learning anything new, really. We're taking it all together. So what does this look like? This is a fraction multiplying another fraction. Because isn't this really I to the 11th over 1? Do y'all remember that? Multiplication of fractions all the way back in the first week. So if I'm going to treat this as the multiplication of fractions, what do I get? How do we multiply fractions? Going all the way back. Straight across, right? So if we do straight across, this becomes, in the numerators, 40I to the 11th over 5I to the 5th. What can we do from here? Well, what did you do in the past when you had letters and numbers in the top and bottom of a fraction? Remember the rule?
Oh, do you divide
subtract.
40 by 5 and then subtract the...
Yes. That's the quotient rule. The quotient rule. So simplify your 40 over 5 like you normally would, and 40 over 5 gives us 8. And what do we do with the i's? What does that become?
6?
6.
Wait, I couldn't hear you.
6.
6. You subtract the exponents top minus bottom, giving us I to the 6th. Perfect. Then translate your I to the 6th. Do your rotation, your pattern. Go around your clock. So I to the 6th, so you bring your 8 down still, but I to the 6th is 1 rotation, 2 more steps. So what does I to the 6th become? We were to do our clock.
Oh,
-1.
-1. So I to the 6th becomes -1. So we multiply 8 times -1, giving us the final answer. This whole thing reduces down to, -8. So what did we do here? You took your rules of fractions for multiplying. You took your quotient rule from about a week or so ago to subtract the exponents, to simplify the fraction to subtract the exponents, and then you just applied your new rule about the rotation going around the clock. That's it. It's those 3 things. But 2 of those things you already knew. So we're mashing up the new stuff with your old stuff. Okay, always keep that in mind. Your old stuff is still coming into play. Questions on this one? Hopefully you're finding it not too terrible. It's just a matter of what? Remembering all your rules.
yeah.
That's the thing, isn't it? It's you have all these skills and rules that you've learned, and they're all coming together. And that's in a sense what you're continually doing is practicing your old stuff with your new stuff. And that's on purpose, by the way, because that's how you're going to learn your old stuff, is having to apply it to your new stuff too. So just keep those things in mind. It looks like fractions. Oh, let me multiply it looks like the multiplication of fractions. Apply your rules for that. Oh, wait a minute. I got i's on both sides. I did that before. Quotient rule. And so that's kind of the way to sort of think about that. Okay. This one also applies old stuff. So it's going to take your old stuff and apply it to new stuff. But there is one new thing here. When it says simplify the expression here, what we want to do, and the thing to take note of, is we have an I down in the bottom. we don't really like i's in the bottom. I don't know why. We just don't like to do it. So we're going to quote rationalize, that's what it's called, rationalize the denominator. Rationalize the denominator. And so what does that mean, to rationalize? All it means is we're going to take a fraction here. Now, we can multiply the top and bottom of a fraction by anything. You know, if we multiply by 1, you know, we can multiply the fraction by anything. Why? Just so long as we do the same thing in the top and the bottom. So the way that we're going to do this is you take the exact same thing in the denominator, but change the sign in the middle, okay? So we're going to say 5 plus 4i. Whatever you do to the bottom, you got to do to the top. So we're also going to do a 5 plus 4i to the top. And so what do? Well, we have the multiplication of two fractions. So let's write it as the multiplication of two fractions. 5 plus 4i times 5 plus 4i on the top. All of that over 5 minus 4i times 5 plus 4i. Now, you don't want to cancel because that would sort of defeat our purpose. What you want to do is go ahead and multiply. And how do we multiply these things? How would you multiply, say, at the top? What's the
Do you
process?
distribute? Or do you do what we just did where you do FOIL?
Yep. That's exactly it. You're multiplying binomials. Multiplying binomials. And the interest, well, so you apply your, yes, let's put it in shorthand. That's the FOIL method, or the distributive, Jackie, exactly right, distributive property that we were talking about, that you did in a prior lesson. So if we were to apply FOIL to the top, what do we get? 25, plus 20i. I'm going to run out of room. So this becomes 25 plus, so the outer is 20i, the inner is 20i, and then the the last is 16i squared. Good. All of that over first, outer, inner, last. So first 25 outer plus 20i, inner minus 20i, last minus 16i squared. At this point, combine your like terms. So in the top, we combine the like terms, the two 20i's. So that's going to give us 25 plus 40i plus 16i squared. Down at the bottom, plus 20i minus 20i becomes what? Or what happens to them? Yeah, good. Like the goose egg. Yeah, these two terms right here go away. They cancel with each other. And that was actually by design. That's why we did it. Was by design because we changed the sign in the middle. So this becomes 25 minus 16i squared. Normally, you would be done at this point, but we're dealing with i's. So you got to always check yourself. Can I simplify the i's anymore? Can I
40 and
simplify
60. 16, sorry, 40 and 16 can be added together since they're on the same side together, right?
close? But remember, if you have 3x and you're adding 5x squared, can you combine those?
Yeah.
They're not like terms. Remember, they need to be identical.
Oh,
They need to be
yeah,
identical.
adding to it.
But
Okay.
you always want to look to see, are they like terms? So no, they can't. The 40 and the 16 I cannot combine. But what do we know about I squared? Where on the clock is it? Isn't it -1? It's the second step of the clock. It's at the 6 o'clock period. So what we can do is bring the 25 and the 40i over. But 16i squared becomes what? 16 times -1. And then same thing down at the bottom. Change that I squared. So it becomes 25 minus 16. Oops. Times -1. So now what? Well, I'm going to clean this up a little bit. This 16 times -1 on the top gives me, oops, I could have just left that there. -16. And then this 16 times -16 times -1 here gives me +16. And so I can simplify this to be what? 25 minus 16 in the numerator gives me, I don't know, 9 plus 40i, and 25 plus 16 in the denominator gives me 41. So this is just, I'm going to write it up here now. That's the answer here up in green. So what did we do on this problem? This was the key. This step right here is the key. You just multiply the top and bottom by the same thing being whatever is in the denominator, but just change the sign in the middle. Then apply your FOIL process. This is the FOIL process here. And then the rest of it was just combining like terms and applying the fact that your I squared is the same thing as -1. So again, this is also a mashup. Up here was the new step, multiplying the top and bottom by the 5 plus 4i. The rest of it was a bringing forward stuff that you reviewed in, I think, last week. FOIL method, combining like terms, and then the I squared. Go for it, Ivy.
Yeah. So can you remind me where the 9 came from? The 9 plus 41?
Let me make sure I'm right.
Oh.
Yeah. Okay, it's this one right here. 25 minus 16. Because those are like terms.
Okay. And also, my first instinct would have been to just cancel out the like terms, like of course 4i over 4i.
Yeah. Boom.
Or
boom.
later on the 16,
Call it a
like
day,
16i
-1.
squared. Right.
You
Oh,
it's tempting to want to do that, but we can't. Why? Because of these things in the middle, the pluses and minuses. If you reflect back, when you did fractions, when you simplified fractions and you canceled from top and bottom, let's take an example like, uh, not 4. Yeah, let's do 4. Fine. 4 over 10. Why could you cancel is because when you're doing this, you're really treating the 4 as 2 times 2, and you're treating the 10 as 5 times 2, and you're canceling those 2's. What allowed us to do that? What's the operation between that? Multiplication. So the process of canceling is you're breaking it up into factors that are multiplying each other. When you have something like this, they're not multiplying each other. 5 plus 4i, 5 minus 4i. And that addition subtraction makes it so we can't break it up. So when you see, in the larger scheme of things, when you see addition or subtraction, think of them as being married to each other. Okay, they're a unit. 5 has to go with the 4i. Wherever 5 goes, 4i is going to tag along with it. And if you're going to get rid of 4i, you better have something to get rid of the 5 too. But it has to be identical. 5 plus 4i is not identical to 5 minus 4i. They're close, they're cousins, but not close enough. And we'll see that more and more as we go along. There's another lesson where we're going to have it in a similar sort of thing. So one thing to take away here, when you're dealing with I, the really new thing is this clock feature. I minus I 1, I minus 1, and then minus I. The clock feature is the new thing, okay? But otherwise, you treat the I like a variable, like X, like Y. And so all your rules for combining like terms, all your rules for FOIL method, all your rules for doing that still apply. You treat the I like a variable, and the only time you don't treat it like a variable is when you have something like this, where you can translate it to the clock. If you can translate it to the clock, back to the clock, you want to do it. So in other words, we don't like exponents over i's either. We either want it as a plain I or a 1, something like that. You want to put it back to the clock. So not I squared, not I cubed, not I4. Put it back to the clock.
Okay. Thank you.
So this one seems long, but really it brings everything together. Let me see the next one right quick.
Does I squared stand for something in particular? Because we used to be able to leave, like x squared or y squared or something like that as its own,
I
but
squared means,
special.
I squared does mean something in particular.
Okay. Some sort of
-1.
Yeah, but does x squared mean anything in particular?
No. I is special. I is the only thing that has a definition to it of a specific value. And it's
Okay.
because of that specific value that I squared also has a specific value. Oops. But otherwise, a generic X or a generic Y, no. I is the only thing that has a value.
Okay. So when I'm writing an algebraic expression, I probably shouldn't use I
Don't ever
as
use
a
I.
variable
No.
unless I need it. Okay.
I is special. Right.
Okay. Thank you.
Okay. So uh, so this actually just goes back. This here is really the same thing we've done before. It's just instead of negative, you drop the negative, write it as an I, and then simplify the remainder like you always did, like you did in the prior lesson. Okay? So what this boils down to then is you just simplify this part. Take the negative, pull it out as an I, and then simplify the radical as you would do in the prior lesson. So when you're dealing with I, just translate it back to its circle and then simplify as you would in the prior lessons. Sometimes you'll have to simplify a radical, sometimes you'll have to simplify a fraction, but you're basically taking your other lessons and applying them here. That's what it boils down to. Okay, well, I'm going to go ahead and step out here. What I encourage you to do is take this time to work on wherever you're at in the assignments. So hopefully you're done. Hopefully you're near done with this stuff or done with it. And so this, and then maybe this. Work on those with the time that you have, and then tomorrow. So I'm going to start. We're going to start reviewing tomorrow with factoring, rules of exponents. We're going to bring all that back, get you ready for the test that's coming up. But we're also going to bring in our other stuff of quadratics too. And all this is leading up to, by the way, all of this is leading up to this.
We're doing the test Tuesday, correct?
No, not next Tuesday. Aren't we on fall break?
Okay.
It's October 30th.
All right.
Okay. That's when we're going to set it for. So all this stuff is leading up to this, where we're going to take this and apply it to quadratics. That's the ultimate part where it's all leading to. And once we get to quadratics, we'll cut it off there. Okay. So shoot me your questions as you work on everything. You're gonna have questions. Happy to help out, and then we'll catch up tomorrow. Okay.
Okay, thank you.
I have one more thing to say before you go. I'm so sorry. I had emailed you a couple of days ago telling you that I'm not going to be able to make it to class tomorrow. Is there any way that you can record the lesson so I can go back and look at what y'all did?
Yeah, that's what I'm doing. I'm recording them each night for y'all.
Okay.
And I just got to post the one yesterday. I forgot to.
That's perfectly fine. Thank you so much.
Sure thing. Sure thing.
Mm.
All right. Have a good one. Bye.
Y'all too.